In the last video I showed you this unstable system. It flipped and then crashed. Only when we added a state feedback controller we managed to stabilize it. At first it might have looked like we simply tuned the gains of the controller, but that's not what happens here. We didn't tune a controller, instead we used a controller to change the structure of our system matrix. And even though this is a control engineering video, I am going to show you in fewer than 10 equations over the next 3 minutes why this approach works and what we are actually doing. In fact, let's count them as we go. Let's build up what a state feedback controller does from the beginning. We start with the standard state space description of a linear system. This equation tells us how the state evolves over time, based on the system matrix A in connection with our state, and how the input U influences the system over the input vector B, here for a system with a single input. If we introduce a state feedback controller, we no longer calculate the input based on a single error like we would do in a PID controller. Instead, our input is a linear combination of the error that exists in all states, weighted by our gain vector k. On its own, this equation does not tell us anything about how it works. The key step is to insert this feedback law into the original system equation. If we do that, we obtain this expression here. And now comes the crucial reshuffle. We can factor out the state vector x and rewrite the system as x dot equal to a minus p times k in brackets multiplied by x. Even without analyzing the math in detail, you can see that this looks very similar to our original system, at least structurally. It still has the form change of our state is equal to a matrix times the state itself, but there is one decisive difference. The matrix of the controlled system is no longer just the original system matrix A. It is now A minus BK. With this, our dynamics depend directly on the controller gains K, meaning we can deliberately adjust the behavior of the system. This is not a small modification, it is a structural change to the system. In the original system, the dynamical behavior is completely dictated by the poles of the matrix A. Now take a look at the closed loop system with the controller. Its dynamics are no longer governed just by A, but through our controller by A minus BK. And this means that the poles are no longer fixed by physics alone, they can be moved. Through the gain vector k, we can shift those exact poles to new locations. Meaning we can kind of cheat physics a little bit here. If the poles of the original system without controller cause the state to rise uncontrollably because we are in the unstable region, we can now choose our gains in such a way that the new poles move over into the stable region. And once they are there, errors in the system no longer grow, they decay to zero. And this is the central mechanism of state feedback control. Now that we understand what happens here mechanically, let's look at a concrete numerical example. The system we use here is not a specific physical machine, but a simplified model chosen to illustrate the concept clearly. We can now rewrite them to achieve our state space form of the system. From this representation, we can compute the poles of the uncontrolled system, that is, the eigenvalues of the matrix A. They are located at the following positions in the complex plane. We have a complex pair at -5 plus -2 times I and one at +2. Notice that one of these poles lies in the right half plane and that immediately tells us the system is unstable. We will go deeper into the math while this is in a follow-up video. For now, we just confirm this by simulation. If we run a simulation with the controller turned off, our input remains at 0. However, the states grow to infinity over time nevertheless, instead of going down to 0. Not what we want to see. This is the system crashing. Now we activate the state feedback controller and start to move the unstable pole to a new location by calculating suitable gains. We leave the response of the uncontrolled system in the background for comparison and add the simulation result with controller on top. As we shift the unstable pole across the imaginary axis into the stable region on the left half plane, the system behavior changes fundamentally. The trajectories no longer diverge, they start to decay towards zero. First very slowly, as the results where we barely cross the border show, but as we move the poles further and further, it decays faster. Now our system has become stable thanks to the controller. We must be careful here though. If we start to move all of our poles too far from their natural location, the control input increases significantly. The system reacts faster, yes, but at the cost of much higher input effort. This is not only bad because we require a higher input, any uncertainty in the system not taken into account in planning also has a greater impact. State feedback gives us authority over the dynamics, but it does not remove trade-offs. Pole placement is therefore not just about stability, it is about choosing a reasonable balance between performance and effort. Let's go through the results again quickly, since you know what each of them is now, because it is quite beneficial for understanding. At first, we ran the system without any controller, and since we have one unstable pole at +2, our states start to grow uncontrollably. We are not using a controller here, so this is purely due to system instability. Then we started moving the poles. As we leave the unstable region, we are able to control the states, and they no longer grow uncontrollably. Hitting 0 with a pole and having 2 negative ones means we have a residual error in our states, but at least it no longer grows uncontrollably. As we move the pole a little further to the left, the error actually starts to decay and heads down to 0. But since we have crossed the boundary just barely, it subsides very slowly. Then we move the pole further into the stable region. Here the error starts to subside quicker. This is us controlling the system like we want to. If we overdo it and start to move the poles all the way very far to the left, our error over here subsides very quickly. This comes at a huge controller action at the start, as you can see here. We will cover more of the math behind that and the study related to parameter uncertainty later on. So if you haven't already, now would be a great time to subscribe. It is obviously not all roses and rainbows. There are some challenges we did not cover so far. I do not want to call them limitations because there are solutions for it. In order to be able to apply something like this, we need to know the entire state of our system. Either via direct measurement, which tends to be too expensive or simply not possible, or by application of an observer where we construct the state from limited measurements. Let me know in the comments if you are interested in this topic. A little bit more in the direction of limitation is the next thing, being that state feedback theory in this form applies strictly to linear systems. Most real systems are non-linear, at least partly or some part of it. So we need to take an extra step. The calculated gains and theory do not apply globally, but only in smaller regions acting linear. So instead of applying it directly on a global scale, we have to linearize the system around the point where we want to stabilize it, our operating point. In a sufficiently small neighborhood around this operating point, many nonlinear systems behave approximately linear, and we can apply this theory. We will explore that process and its practical implications in a later part of this series. Let's quickly summarize what we have learned and look at what is about to come. By introducing the feedback law, we transformed our original system matrix A into the closed loop matrix A minus BK. The gain K allows us to adjust the poles of this matrix deliberately and turn an otherwise unstable system into a stable one. In other words, K allows us to define and set a new, more desirable system behavior. And this exact step is the core of state feedback control. In the next videos, we will explore the mathematical meaning of poles, why they have such a decisive influence on the system behavior, and how the matrix algebra behind them can lead to counterintuitive effects. For example, situations where a mode that should decay faster actually takes longer to reach a defined error limitation, because the matrix interactions push its starting values much higher. From there, we will move on to computing the gain vector k and the study of parameter uncertainty. Thank you very much for watching, and I'll see you in the next one.